Hello. Today we're going to talk about conservation of energy with work. Okay. And if you need to, please pause the video for a sec and just kind of copy down all this review stuff that we've talked about in the past. All right. So, quick review. So, first we have how to calculate work done by a force. That's the work equals force times distance. Remember, that can be a plus, a minus, or zero, depending on if the force is with the motion, against the motion, or perpendicular to the motion. Okay, so plus is when the force is with the motion, minus is when the force is against the motion, and it's zero if the force is perpendicular to the motion. And we've done a whole bunch of examples with that. And then the other equation, the real long one I have there, is our conservation of energy equation. And a quick reminder, so you've got kinetic energy. If something's moving, it's got kinetic energy. You've got gravitational potential energy. If something has height, it's got gravitational potential energy. You have elastic potential energy. So if there's a spring or a rubber band that's compressed or expanded, then you have spring potential energy. And then you have work. And that's work done by a force. And I've listed the four that we might encounter for our problems: friction, applied forces, normal force, and tension. And that is when mechanical energy is converted to some other form, like heat or vibration or sound or chemical or something, or vice versa. So for instance, if I am pushing a box, I am doing work on it, and my chemical potential energy in my body from the food I ate is turning into something else, probably kinetic energy or maybe some gravitational potential energy. So for us, more than likely, we're going to encounter friction, which is going to make negative work usually. So that's taking mechanical energy out and turning it into heat. And then in our last example, in the second video I'm going to show you, there's going to be work done by an applied force. A person is going to be doing work. Okay. So in the previous examples, this W was zero. Well, now it's not going to be. Now there's going to be something to put in there. Okay. So I'm going to walk you through a couple examples on this video, and then I got a second video with another couple examples for you. So first example, and we'll call this example 1A. Okay. So this is an example we did previously where you had a book, had a mass, and we dropped it. And the height we dropped it from was 6 meters. Okay. And we used conservation of energy to calculate how fast the book was going right before it hit the ground. And just so you remember, that velocity that we got was 10.8 meters per second. Okay. And in that problem, I don't think I gave you the mass of the book because it turns out they cancel out. Well, for this problem that we're going to do now, the mass won't cancel out. So I have to give that to you. So let's say it's a 2 kilogram book. Okay. And let's say in this problem, it's the same problem, except there's going to be some air resistance, some air friction acting on the book. And let's say that force of friction is equal to 5 newtons, okay? And that force of friction is going to point against the motion, okay? So that's going to do what sign of work, positive or negative? Well, it's going to do negative work because while the book's moving down, friction points up. That's the opposite direction. So I'm going to have a W term. It's going to have a negative sign in front of it. All right, so we're going to start at position A, and then we're going to look at position B, and we're going to look at our conservation of energy equation. At position A, is the book moving yet? Well, no, so there's no kinetic energy. Does the book have height? Well, if we call the ground zero, which kind of makes sense, then yes, you're going to have gravitational potential energy, so there's going to be an EG up there. And is there going to be work done by any forces that are not already in gravity, spring, or motion? Well, yes, there's going to be work done by friction. So I'll put a plus WF for friction. Now, that's going to be a negative value, and I'll get to that in a second. At position B, right before the book strikes the ground, is it moving? Does it have kinetic energy? Well, of course it does. It's moving. Okay, we're trying to find the final velocity and compare it to our 10.8 from before. Does it have any potential energy? Well, does the book have any height at point B? Basically, no. It's all right, getting ready to touch the ground. And in both before and after, there's no springs or anything, so there's no elastic potential energy. So there's our equation. So on your worksheet, you're going to see 3 boxes. That's what you're going to put in the first box. In the second box, you're going to sub in the equations for each of those. So EG is mgh. The work done by friction will be minus, because friction is acting against the book. And the equation is force of friction times delta x. Okay, that's your work. That's how you calculate work. That's from our review. Okay, work is force times delta x. And this equals kinetic energy. And the equation for kinetic energy of the book right before it hits the ground is 1/2 mv squared. Now a note here. Can we cancel the masses out? The answer is a resounding no, because you would have to have an m here, an m here, and an m here to cancel them out, and we don't have that. We don't have an m here, so we cannot cancel the mass out. That's why I had to give you the mass of the book in this case. So your second box would look like this, okay? And then on your worksheet, there's going to be a third box, and that's where you're going to plug all your numbers in. Okay, so m is 2, g is 9.8, h is 6, force of friction is 5. The book travels 6 meters. So in this case, by the way, and I'll make a note of that, delta x and h, in this case, they're the same thing, okay? Then we have equals 1/2, the mass of the book is 2, and we're trying to solve for velocity squared. So on your worksheet, you're going to have 3 boxes. That's what you'd have in those 3 boxes. Underneath the box, it'll say something like do the math, okay? So if I do the math here, if I plug these numbers in the calculator, I get, let's see, this is 117.6 minus 30. 1/2 of 2 is 1, and then we got our v squared. So you get 87.6 equals v squared, and you get a velocity of 9.36 meters per second. You will note that is less than what the velocity had been without friction, and that should make sense. If you got friction, it's going to make the book not go as fast. It's going to try to prevent the book from moving, so it's not going to, the book won't gain as much kinetic energy. All right, so that's our first example. Now there's a 1B on this. It's a tweak on 1A here. So we'll call this example 1B. Let's say same book, same height, all that stuff. So here's our book. Same mass of 2 kilograms, same height, okay, of 6 meters. Okay, we're going to drop the book this time. But this time, what we're going to say is right as the book is getting ready to hit the ground, the velocity there is 7 meters per second, okay? And I'm going to ask you to find 2 things here. I'm going to ask you to find the work done by friction, and then I'm going to ask you to find the force of friction. So I'm asking you to find 2 things about friction. 1, the work done by it, and 2, the force of friction, okay? Now, this problem starts off exactly the same as the previous problem. So we had gravitational potential energy to start. We've got some work done by friction. And then after, when the book's getting ready to hit the ground, it's moving, it's got kinetic energy. So that would be your first box. Our second box is going to look almost the same, except for the following. Oops, and that's a mistake. EG is mgh, okay? We're trying to find W. Work done by friction is just W, so just leave it as W, okay? Work done by friction. We're trying to solve for that number. And then kinetic energy is 1/2 mv squared, okay? Now, that would be your second box. Your third box, we're going to plug in our values. So like this first term is exactly the same as it was before, okay? But now we're solving for WF. And we got a 1/2, and mass is 2, and your velocity is 7, and we got to square that. So that would be what you'd put in your third box. And then after that, there would be all the math. So like this first term is 117.6 again. We're trying to solve for WF. And then this is 49. And if you subtract 117.6 from both sides, you get the work done by friction is negative 68.6, and work is measured in joules, okay? Now, it should be negative. Friction's sucking energy away from the book and turning it into heat. So that's why you get a negative, and also the math gives you a negative. Now, finally, they ask for what's delta x? or I'm sorry, what's the force of friction? How much is friction? Okay. So we have an equation for work. Work is force times delta x. I'm asking you for the force of friction, so here's our unknown. We know the work, it's negative 68.6. We just calculated that. We're trying to find the force. We don't know that. And we know delta x is 6, okay? So if you divide both sides by 6, you get the force of friction. Force of friction is negative 11.4, and it's a force, and it's newtons, okay? Now, the only deal with the negative, it just means that this force is acting against our motion of the book. The book's moving down, friction points up. Sometimes I'll just ask you for how big is the force, in which case you don't have to put the negative there if you don't want to. All right, so the next video will show you a couple more examples. I hope this is helpful.